This is Physics 2120, Lecture 10. Today we're going to talk about direct current circuits. So when the current in a circuit has a constant magnitude and direction, the current is called a direct current. Because the potential difference between the terminals of a battery is constant, the battery produces direct current. And a battery is also known as a source of EMF. The EMF, or the electromotive force, of a battery is the maximum possible voltage that the battery can provide between its terminals. The EMF supplies energy. It does not apply a force. And the battery is normally the source of energy in the circuit. So, if I want to look at a simple circuit, we're going to consider that the wires themselves have no resistance. We know that they do have some resistance, but it's going to be so small compared to any other element in the circuit that we're going to be able to neglect it. So the positive terminal of the battery is at a higher potential than the negative terminal, but there is some internal resistance in a battery also. So if I were to really look at a battery, in the box here, we consider our battery. Little r here is our internal resistance. And if the internal resistance is 0, then the voltage across the terminals is the same as the EMF. But in a real battery, there's some internal resistance. So the terminal voltage, delta V, that's the potential difference between A and B, is equal to the EMF of the battery minus IR of the battery. So that means, depending on my current through the battery, the potential difference across the battery terminals could change. So the EMF then is equivalent to the open circuit voltage. That's the terminal voltage when no current is in the circuit. So if I hooked up a voltmeter to a battery not in a circuit, that's the voltage I would read, is the EMF. The actual potential difference across the battery then is going to depend on the current in the circuit. So the terminal voltage is the voltage across whatever this external resistance is. That external resistor is called the load resistance. And in the previous circuit, the load resistance is the external resistor. But the load resistance could be any electrical device. It could be a heater or a motor or anything put in that has resistance and is in the circuit. Then the total power output of the battery, as power is I delta V, which is I times E, the electromotive force. This power is delivered to the external resistor, I squared R, and to the internal resistor, I squared little r. So, IE across the battery is I squared R plus I squared little r. So, how do I deal with resistors connected in groups? Of course, we learned about capacitors in series and parallel. We're going to need to consider resistors in series and parallel. So we have two or more resistors are connected end to end. They're said to be in series. And for a series combination of resistors, the current is the same in all the resistors because the amount of charge that passes through one resistor must also pass through the other resistors in the same time interval. Then the potential difference will divide among the resistors such that the sum of the potential difference across each individual resistors is the total potential difference across the sum. So potentials add. Delta V from A to C is equal to the delta V from A to B and then from B to C. And I know that the potential difference across each resistor is IR. So delta V is equal to IR1 plus IR2, which is just I times R1 plus R2. It's just a consequence of conservation of energy. The equivalent resistance has the same effect on the circuit as the original combination of resistors. So what would that look like? So, if I wanted to replace these with a single resistor, I know I times R1 plus R2 is equal to I times R equivalent. That's a potential difference across A to C. So then R equivalent is just R1 plus R2 plus R3. The equivalent resistance of a series combination of resistors is the algebraic sum of the individual resistances and is always greater than any individual resistance. If one device in the series circuit creates an open circuit, all devices are inoperative. Now, when I have resistors in parallel, we know the potential difference across each resistor is the same because they're both connected across that same battery. The total current that enters one side of the series has to equal the total current going through all the resistors. The currents are generally not the same because I only have so much charge that I can distribute and so much charge going through each resistor as a function of time. So, if I have them in parallel, I know that the resistance, I know that the voltage across each one is the same. And I know the voltage across this equivalent resistor is the same as each individual one. Now, this method of wiring things is how household circuits are put together. The household is wired so that electrical devices are always connected in parallel. That ensures that the same voltage is delivered every time, and that if I have too much current going through so things are getting too hot, I can have a circuit breaker that will stop the current in one circuit but won't stop it in all the circuits. So to find the relationship for equivalent resistance of parallel, I know that the current going through here has to be this current going through each branch. So I is equal to I1 plus I2, where I1 is the current going through resistor 1, and I2 is the current going through resistor 2. And I know that delta V over R total, the equivalent, is I. Delta V over I1 is I1, and delta V over R2 is I2. So the delta V is the same in each case, those go away, so 1 over R total is equal to 1 over R1 plus 1 over R2, or for however many resistors I have. The equivalent resistance of a lot of parallel resistors is 1 over R1 plus 1 over R2 plus 1 over R3, on and on and on until we have all of our resistors taken care of. The inverse of the equivalent resistance of two or more resistors connected in parallel is the algebraic sum of the inverses of the individual resistance. The equivalent resistance is always less than the smallest resistor in the group. So in parallel, each device operates independently so that if one is switched off, the others remain on. In parallel, all the devices operate on the same voltage, and the current takes all the paths. The lower resistance paths will have the highest currents. However, even very high resistances will have some current. So when looking at a problem like this, we treat it in the same methodology as we did combinations of capacitors. We look at where we can combine them and redraw it each time. So for example, the 8 and 4 ohm resistors are in series, and we can replace that in our circuit diagram with a 12 ohm resistor. The 6 and the 3 ohm resistor are in parallel. So 1/6 plus 1/3 is 3/6, which is 1/2, and we invert that and we get 2 ohms. And then these two would be in series, so we can complete the whole thing with a 14 ohm resistor. So it looks like I have a font problem. These all here should be ohm symbols. Now, there are ways that we can connect resistors together that we can't reduce them into a single equivalent resistor. So, if I have a case like that, and I want to know what the current and voltage across every item in my circuit is, I might have to use another method. And the method that we're going to use has two rules, and we call those Kirchhoff's rules. So the two rules start with the junction rule. The sum of the currents entering any junction must equal the sum of the currents leaving the junction. It's a conservation of charge. Whatever goes in has to come out. I can't build up charge or deplete charge in a junction. The second is the loop rule. The sum of the potential differences across all the elements around any closed loop must be zero. That just says as I go across each individual element, I'm either going to gain energy or lose energy. When I come back to where I started, I can't have a different energy, so the total steps up and down in energy around a closed loop have to be zero. Mathematically, it says the sum of the currents going in is equal to the sum of the currents going out. And the loop rule says add up the delta V's around a closed loop and you have to get zero. Again, the junction rule is all about conservation of charge. And you can kind of think of it as water flowing in a pipe. If I have so much water flowing in this pipe, what flows out of this pipe the amount of water per time flowing out has got to be the same as flowing in. If more flowed out than in, all of a sudden I would have no water in my junction. That doesn't make sense. If more flowed in than flew out, then I'd have a buildup of water and the pipes would burst, and we can't have that either. So what goes in must come out, is all that we're saying about the junction rule. For the loop rule, the direction that I go around the loop is going to matter. So if I'm looking at the potential difference, I'm going around from A to B, and current is going in the direction of A to B, then the potential difference from A to B is minus IR, because I'm losing energy as I go from A to B. However, if I'm going from A to B and I'm going against the current, the potential at point A is less than at point B. So as I go across this circuit element in this direction, I'm going to get a plus IR. Or if I've got a battery or some electromotive force, if I'm going from A to B, I'm going across this. B, this area is at a lower potential than this potential. So as I'm going across here, the potential difference is plus the electromotive force of the battery. However, if I'm going here, the potential difference of this side is higher than this side. So as I go from here to here, I go down in potential difference. So when I'm solving a circuit using Kirchhoff's rules, I use the junction rule as often as we can, so long as each time we write an equation, we have a current that's not been used in a previous junction rule equation. In general, the number of times the junction rule can be used is one fewer than the number of junction points in the circuit. The loop rule can then be used as often as you need, so long as a new circuit element, either a resistor or battery, or a new current appears in each new equation. And we're eventually going to need to know, have as many independent equations as we have unknowns in order to solve this algebraically. So in order to solve a particular circuit problem, the number of independent equations you need to obtain from the two rules equals the number of unknown currents. Any capacitor is going to act like an open branch in the circuit. The current in a branch containing a capacitor is zero under steady-state conditions. So we're going to draw a circuit diagram. We're going to assign labels and symbols for all known and unknown quantities. And we're going to assign a direction to the currents. Now, we might not know the direction just looking at the circuit. Sometimes we will. That's okay. We choose a direction, and it might be arbitrary. But if you follow all of the Kirchhoff's rules carefully, at the end, if you solve for a current and you get a negative value for it, you knew you chose the direction in the wrong direction, it'll come out in the end. You'll know the magnitude and direction in the end, whether the current is positive or negative. So then we apply the junction rule to any junction in the circuit that provides new relationships among the currents. We next apply the loop rule to as many loops as are needed to solve for the unknowns. So to apply the loop rule, we have to correctly identify the potential difference as you cross the various elements in the direction that you cross them. And then once we have those equations, we solve the equations simultaneously for the unknown quantities. Again, if a current turns out to be negative, the magnitude will be correct, and the direction is just opposite of the direction you drew in your circuit. So let's work out a problem. This problem, we want to know what the power dissipated in this circuit is. Notice I've got a couple of different batteries in here, and there's no way to really find the equivalent resistances because these two resistors are not in parallel. They've got this battery amongst them. And they're not in series either because I've got a junction in there. So we can't find an equivalent resistance. We're going to have to use Kirchhoff's rules to find the current and resistance in each branch. So we already have our circuit drawn. We know what the resistance of each circuit is. We know where the batteries are, and so we choose some directions. So in this case, we've chosen I1 to be in this direction because I've got a positive battery here. It sort of makes sense that it would go in this direction. It might be wrong depending on the rest of the circuit, but it makes sense. So if I1's coming here, it makes sense. Let's draw I3 down here. I2 I'm going to draw coming down. Even though it's coming out of the negative side of the battery, it might be wrong, but it really doesn't matter. I've chosen certain directions for my current. In the end, when I solve, I'll see if I chose correctly or poorly. So, first thing we're going to do is start applying the junction rule. So, I come around here, B. I've got a junction at B. So I look at the currents going in and the currents coming out. So, going in, see, I got I3 coming all the way around here. And so at B, I3 is going in, I2 is coming out, and I1 is coming out. So that goes out, I1 plus I2, has got to equal I3. So there's one equation. Now I can do this at the other junction at C. And at C I have I1 and I2 coming in and I3 coming out. So I get no new information here. So now I've depleted all my junctions, so now I need to go to the loop rule. I have three unknowns, I1, I2, and I3. I've got one equation, so I need two more equations, so I need to do two loops. And I could do lots of loops. I could do the upper loop, the bottom loop. I could go all the way around the outside. I usually have more loops than I need. I just choose as many as I need and go on. So, let's look at the top. The loop I'm going to choose is B, E, F, C, B. So now, as we start here with our pencil, we're going to go across. We hit our resistor. Now we're going in the direction of I2, so that means I'm going to subtract 4I2 because there's going to be a potential drop across it. Then I get to the battery. I'm going from the positive to the negative terminal, so that's going to be a minus 14 volts. I come along here. Now I'm coming here and I hit another resistor. This time I'm going against the current, so I'm going to increase my potential difference. I get at 6I1. Then I get to the battery, and I'm going from positive to negative, so I'm decreasing potential difference, minus 10 volts, and I'm back to where I started, so the total potential difference between B and B is 0. So now I can simplify things a little bit. 6I1 minus 4I2 is equal to 24 volts. Or at this point I can still divide by 2. 3I1 minus 2I2 is equal to 12 volts. So there I have my second equation. So now I need a third equation, so I'm going to use the bottom loop. So we start at point A. We're going to go to point B. Now I'm going this way. I'm going from negative to positive, so that's 10 volts. I'm going with the current, so that's minus 6I1. And I'm going with the current again, so I get a minus 2I2, and I'm back to where I started. Or 6I1 plus 2I3 is equal to 10 volts, or divide that by 2. 3I1 plus I3 is equal to 5 volts. Now I have my three equations and three unknowns. I can solve these simultaneously. So at this point, the physics of the problem is done. This is all math. And we could do this several ways. We can use our algebra, which I'll go through in a second. You could populate these in MATLAB or Mathematica or another equation solving program. Doesn't matter how you do it. That's the math. The physics is done. So let's go ahead and look at the math real quickly. I2 is equal to I3 minus I1. And I3 is equal to minus 3I1 plus 5 volts. That's this bottom equation here. So 3I1 minus 2I2. I2 we said is I3 minus I1. So we plug that in, is equal to 12 volts. Or simplifying, we get 5I1 minus 2I3 is equal to 12 volts. Now, I can plug this value of I3 in there. I do that, 5I1 minus 2 times minus 3I1 plus 5 volts is equal to 12 volts. So 2 times 3 is 6, the minus signs go away, so 6 plus 5 is 11. 2 times 5 is 10, it's negative, I bring this over, I get 22. I divide out, I get I1 is equal to 2 amps. So we chose the correct direction for I1, and now we know its magnitude. Next we solve for I3. So we know what I1 is, we plug that in here, and we solve for I3, and we get I3 is negative 1 amps. So we know the current in this branch is 1 amp, but the direction we chose was wrong. The direction should actually be there. And finally, we can plug in for I2. We get I2 is minus 3 amps. So I2 should really be in this direction. I3 should also be in this direction. Didn't matter for solving the problem. We know their magnitudes, and now we know the proper direction for each of the currents. So I1 is 2 amps, I2 is 3 amps, I3 is 1 amp. Now we can find the power dissipated by the circuit. Power, we said, is I squared R. So in this upper branch here, I've got I2 squared times 4 ohms, which would be 9 times 4. In this branch, I1 squared times 6 ohms, which is going to be 4 times 6. And down here we have I3 squared times 2 ohms, which is going to be 1 times 2. We add those all together, we get 62 watts is the power dissipated by the circuit. So, to review what we talked about today, talked about resistors and how to combine resistors in series and parallel. Just like we did in capacitors, we have equations to combine them when they're in series and series and in parallel. We can use in parallel that the potential difference across all of them is the same. In series, the current's through the same. So if I needed to figure out potential difference and voltage across each thing, I could do it just exactly like I did in the capacitor problems. But we also said there are some times where I can't combine resistors, and I can use Kirchhoff's rules to solve my circuit, which means the potential difference in current through each part of my circuit. And I have the two rules, the junction rule, current going in is equal to current coming out of a junction, and the loop rule, the change in potential difference across every element in a closed loop is equal to 0.